When analysts evaluate the economics of space access, they rely on a single universally cited metric: dollars per kilogram. That metric is obsolete. The math routinely published by industry observers relies on a remarkably simple calculation. They take a launch provider's minimum advertised base price and divide it by the rocket's maximum stated payload capacity. The equation fails because it conflates two completely different vehicle configurations. It divides the price of a rocket carrying heavy, reusable hardware by the performance of a vehicle stripped of that hardware and flown to destruction. This mismatch between the configuration you pay for and the configuration used to generate the payload capacity masks the true physical and financial cost of getting mass into orbit. By using the expendable capacity denominator, engineers design satellites around a phantom weight allowance. When it comes time to book the flight, they find their payloads exceed the actual limits of the affordable launch tier. To calculate the true economics of modern spaceflight, we have to discard the linear dollars per kilogram curve and subtract the physical mass penalties of reusability. Today, the current baseline for medium lift pricing is the SpaceX Falcon 9. The advertised theoretical maximum of this vehicle is 22 metric tons to low Earth orbit. LEO is an Earth-centered orbit with an altitude of 2,000 kilometers or less. Lifting those 22 tons requires flying the Falcon 9 in a fully expendable mode. All propellant is consumed during ascent, and the booster is destroyed in the ocean. SpaceX's actual base price for a launch is $74 million, but that price specifically purchases a flight on the reusable configuration. The cheapest advertised launch price guarantees a reduced payload capacity. Mission planners cannot buy the lowest price and the highest capacity at the same time. This mass budget bar chart shows the exact penalty of recovery. A rocket has a fixed aerodynamic and thrust profile. To land the vehicle, physical hardware must be added to the structure, which directly displaces customer payload. The vehicle must carry titanium grid fins for atmospheric steering, heavy landing legs for touchdown, and a substantial reserve of return propellant that cannot be used to push the satellite into orbit. These physical additions drag the actual payload capacity for a $74 million launch down from 22 tons to roughly 9.5 metric tons. We can now recalculate the baseline cost using this realistic, reusable payload capacity. We divide the $74 million base price by the true capacity of 9,570 kilograms. The corrected baseline cost is approximately $7,700 per kilogram. Reusability saves millions in manufacturing costs by preserving the booster. However, it passes a severe mass penalty to the customer, altering the dollars per kilogram value. Vehicle configuration is only the first variable. The destination dictates the rest of the equation. Low Earth orbit requires the minimum energy to reach, making it the cheapest possible orbital profile. We can examine Rocket Lab's Electron vehicle as a case study for small lift orbital energy costs. The base launch cost for an Electron is $7.5 million. With a 300 kilogram capacity to LEO, the cost breaks down to $25,000 per kilogram. This animated orbital map shows the payload penalty for reaching a sun-synchronous orbit, or SSO. SSO is a nearly polar orbit that requires the rocket to perform a high-energy plane change to align with the Earth's rotation and the Sun. Executing that plane change consumes excess fuel, dropping the Electron's payload capacity from 300 to 200 kilograms. The price immediately increases to $37,500 per kilogram. The energy requirements are far more demanding for a geostationary transfer orbit. GTO is an elliptical path used to throw a payload tens of thousands of kilometers out toward a final geostationary altitude. Pushing mass that far out requires heavier upper stages on the launch vehicle. If the rocket cannot provide that energy, the satellite must sacrifice its own sensor mass to carry the extra fuel needed to circularize its orbit. Taking low Earth orbit metrics and mapping them onto missions targeting sun-synchronous or geostationary orbits results in budget shortfalls and failed mission architectures. The decade-long era of rapidly plunging launch costs has bottomed out. The physical math is now colliding with macroeconomic reality. Raw materials like aluminum and carbon fiber composites have seen distinct price inflation. Combined with the rising cost of skilled aerospace labor, launch providers have been forced to push their base prices upward. This line chart tracks SpaceX's structured pricing strategy for its rideshare missions, locking in an annual inflationary increase. The 2026 trajectory shows a firm rate of $7,000 per kilogram for a 50-kilogram base payload, up from $5,000 just a few years prior. High-cadence launch providers currently hold pricing leverage over the market. This is driven by near-term manifest constraints and a massive backlog of demand for sun-synchronous orbits. Aerospace procurement teams must now model for continuous, incremental inflationary price increases. Holding out for future discounts is no longer a viable financial strategy. Beyond the launch vehicle itself lies a massive hidden financial layer of spaceflight, the $709 million satellite launch and space insurance market. The deployment of over 6,000 active low Earth orbit satellites has created severe orbital congestion, increasing the probability of high-speed collisions in space. This congestion has directly impacted operator budgets, driving up insurance policy deductibles by 22% as underwriters adjust to the increased risk of partial or total loss. Additionally, new regulatory overhead is entering the market. Starting in 2026, the FAA is implementing payload weight-based licensing fees. The sticker price of a rocket is merely a down payment. You need insurance policies, rideshare adapter hardware, and regulatory risk premiums to form the true operational budget required to achieve orbit. While the dollars per kilogram metric fails to capture the economics of medium-lift rockets, the arrival of super heavy-lift vehicles will move the industry past this metric entirely. SpaceX's Starship is nearing operational status, bringing a payload capability that breaks the linear pricing curve used by the rest of the industry. Voyager Technologies recently filed an SEC 10K document. This filing locks in a dedicated Starship launch for Voyager's Starlab space station in 2029. The contracted price for this launch is exactly $90 million for a payload capacity of 100 to 150 metric tons. We can compare this $90 million single launch cost to the historical assembly of the International Space Station, which required 36 separate space shuttle launches to complete. For only $16 million more than a standard Falcon 9 launch, a single Starship will lift 100% of the International Space Station's total volume in one flight. Mission planners are transitioning from a mass-constrained model to a volume-constrained one. When the capacity floor is raised to 100 tons for $90 million, the exact cost per kilogram becomes irrelevant.